right, let's say that I had a graph where I knew it looked something kind of like this. It went through the point 216 and the point 354. And I wanted to try to model this using some kind of function that would kind of match that curve. I'm noticing that this is passing through the origin, it's concave up, it's increasing rapidly. Maybe it might be like a cubic function or a fourth power function or something like that that's increasing very rapidly. I don't know what it's doing over here, so I don't know if it'll be even or odd or that kind of thing. But this could be a power function, okay? So remember, the general equation for a power function is you have some variable being taken to a power. Okay, so we usually say like x to the b power, and it's got some multiplier a out in front, all right? Same kind of thing as before. You really should be able to substitute different values in. There are only two variables there, so we're just trying to figure out the a and b values, and that means we really should only need two equations, all right? So when y is 16, the x value is 2. Okay, so if I take 2 to the b power and multiply it by a, I'm going to get 16, all right? When y is 54, I don't know the a value, but the x value would be 3, okay? So when 3 is taken to the b power and multiplied by a, I get 54, okay? You could do some different things here. You could, for example, solve for an a variable and substitute into one of the other equations. By the way, a little trick here. You can add the same thing to both sides of an equation. You can subtract two equations. You can also divide. And assuming that a is not 0, which wouldn't really make any sense here because it'd just be a y equals 0 equation, you could divide these two functions, okay? And you could see what you end up getting here. So I think if I divide, it's actually, this is kind of messy. 54 divided by 16, I think it's 3 3/8. Yeah, it's 3 3/8 over here, or you could write it in various forms. But a divided by a is just 1, and I get 3 to the b divided by 2 to the b. I would use exponent rules here and write this a little bit differently. That's the same thing as taking 3/2 to the b power, right? Because that exponent would apply to both of those values. So it's the same thing as 1.5 to the b power. So I have 3 3/8, or 3.375, if that makes you feel better, equals 1.5 to the b power. Now, you might have forgotten how to solve that. That's an equation in which you've got a variable that's an exponent. This is a logarithms problem, okay? And we're going to talk about that a little bit more down the road. It just happened to come up here. It's technically a review, though. So you could write this as log base, remember your base is this number here, log base 1.5 of 3.375 is equal to b, okay? And you might remember the base change formula. You can take the log of this value, and we'll talk about why this is true down the road, divided by the log of this value. And interestingly enough, you get an answer of 3, okay? Kind of nice. So my b value ends up being 3 in my equation here. And actually, I think at that point we have enough information to make this work. You could go back to one of these other equations and put in a 3. For example here, if b was 3, that'd be 54 is equal to a times 3 cubed. 3 cubed is 27. 2 times 27 is 54. And so that means the a value here is going to be 2, and the exponent is going to be 3. And so 2x cubed is our function. And again, I would always try your points. So if I put 2 in here, 2 cubed is 8. 8 times 2 is 16. You can see that that point works out. Okay? Last example. All right, the last one here, let's do a curve that's going to be exponential. So let's say we've got a curve, and it's looking something like this, and it passes through the point 1,6 and the point 218. Okay, and you look at this and you see, okay, it's got a y-intercept, it's not passing through the origin, it's got that kind of J-shaped curve. This could be an exponential function. Okay. Well, an exponential function follows the basic form, y equals, we could say something like a times b to the x power, okay? My variable is my exponent, or my exponent is a variable, okay? Same kind of thing, I can just substitute everything in here. So when x is 2, y needs to be 18. So y is 18, and x is 2, there we go. And when x is 1, y is 6. Okay? And anyway, same kind of thing as before. I noticed that if I divide these equations, a divided by itself is just going to give me 1. So I'm going to divide. 18 divided by 6 is 3. A divided by a is 1. B squared divided by b is b. Look at that! B is equal to 3. And at that point, we could probably figure this out. It's going to be a times 3 to the x power. So let's see, if I have the point 1, 6, when x is equal to 1, I'm supposed to get an answer of 6. This would be 3. 3 times 2 is 6. And so my a value ends up equaling 2. And my final equation would be y equals 2 times 3 to the x power. And again, you could check those points, you could get it to work out. So the strategies tend to be the same. How you actually solve your systems is going to vary a little bit from form to form. But if you know those general equations, you should be able to substitute some points in, and you should be able to come up with something that'll work. So hope those examples help a little bit.